A function is continuous on the closed interval from -5 to +3, such that f of -5 is equal to 3 and f of 3 is equal to -1. The functions f' and f" have the properties given in the table below. Sketch a graph that satisfies the given properties of f. To begin, let's actually start by plotting our endpoints. Our function is defined on this closed interval from -5 to 3, and we know that f of -5 is +3, so we can go to -5, +3, this point right here, and plot it. We also know that f of 3 is -1. So at 3, we can go down to -1, and those are going to be our endpoints. Now let's talk about reading the table and making rough sketches directly below the table and then transferring it over to our graph. So we're given that at our endpoint of -5, our derivative is 0, and then f" is negative. If our function f was continuous, you could consider this a relative maximum and it would have this type of behavior. Now, since we are on this closed interval, the section here to the left, we're going to erase it. This will be a point that appears, but it is now no longer a relative maximum. So it has this horizontal tangent that's concave down, and then it goes into a curved section from -5 to -2 that is negative for the first derivative, meaning it's decreasing, and it's negative for the second derivative, meaning it's concave down. So it's going to look something like this. When we get to x equals -2, we have that the derivative and second derivative does not exist. Now this could create a cusp, a vertical tangent, corner, something of that nature. Based on what we've done here in this rough sketch, it looks like it's going to appear to be a cusp, but we can double check that by continuing in the table. From -2 to +1 for x values, we have positive, meaning it's increasing, but the second derivative is negative, so it will still be concave down, so it'll look something like this. So yes, at x equals -2, it looks like we're going to have a cusp occurring there. Okay. Now if we look at x equals 1, we have a 0 first derivative that is negative. That means it's a relative maximum. So we have this point, and on this side it's going to look like this. It's going to kind of look like this over on the right side of it. And then if we continue in the table from 1 to 2, our first derivative is negative, meaning it's decreasing, and our second derivative is negative, meaning it's concave down. So we're going to again have that similar path to what we drew over here. And now at x equals 2, it's still decreasing, but then the second derivative is 0, meaning we're going to have a point of inflection. So like at this point, we're going to have something going from here and then switching gears. See how the concavity switches. It goes from concave down to concave up. And that should be verified here. From 2 to 3 for our x values, it's negative, meaning it's decreasing, but it's positive for the second derivative, meaning it's concave up. So it is going to look something like that. And now at our endpoint, x equals 3, we have a 0 first derivative and a positive second derivative, meaning it is concave up. If our function f was continuous, you could consider this to be a relative minimum, and it would appear something like this. Now again, since we have this closed interval and it is stopping, it is not a relative minimum, but it has that type of behavior as you approach it. So now we have the general overall shape of what's happening, and now let's transition to actually make our graph. So we're starting at -5, 3, and we're decreasing and concave down until we get to x equals -2. Okay, and then here we're going to then start to increase and still have it be concave down. At x equals 1, we're going to have that horizontal tangent. So I'm going to plot a point right about here. So that'll be my relative maximum that I do have in this continuous function on the closed interval. And then it's decreasing and concave down again until we get to x equals 2, which is right here. And now this is our point of inflection, and it's going to still decrease but switch gradually to concave up. So here's our point of inflection right there. So that's a rough sketch, and let's see how close we are to the answer in the tab. That's pretty close.